Hello, everyone. Today we're going to be talking about the binomial distribution, and this distribution is probably one of the most common distributions in statistics, and it's really a, uh, a probability concept because it is a probability mass distribution, PMF, or PMF, probability mass function, and that means it uses a discrete random variable. Now, first, let's just go over what a. I'm gonna start here. So it's called a binomial distribution, with there's two parameters, n and p. Now, when I first learned this distribution, I thought n and p were both parameters, but it turns out n is not a parameter. P is a parameter. N is number of trials. Okay, and but the binomial distribution is an adaptation or an extension of the Bernoulli trial, which is just P. Let's start with the Bernoulli trial, and then we'll work our way up to the binomial. Okay, what is the Bernoulli? What are the assumptions of the Bernoulli? Let me give you an example. Let's flip a coin. That is the most classic example because a coin toss has two distinct outcomes. It has a heads and it has a tails. Now, let's say we're interested in the number of heads. So we flip a coin one time and we get whatever, a heads or a tail. Now, X is a random variable. Okay? It's a random variable such that it can take values 0 or 1. Because we either get a heads, and that's a 1, or we get a tails, and we get a 0. Okay? Two distinct outcomes for Bernoulli. Notice we're tossing this coin one time. If we were to toss this coin many times, then we would have a binomial distribution. And we'll talk about the assumptions of the binomial in a second. But intuitively, how would you think this probability mass function should look like? Right? So Bernoulli, what should it look like? Well, what is the probability of getting heads? Well, in reality, many people might question if it's a fair coin or not, but in probability, notice how I said this is a probability concept. We already know, let's just say we know that it's a fair coin. Okay, let's just say 0.5. It's a 50% chance that we'll get a heads. But what about the other 50%? Well, we got 0.5 here. But how do we make sure that if we flip a heads, that we get the 0.5 here? Well, let's denote x. X can take the forms of 0 and 1 because it is a random variable. Notice, okay, a quick side note for random variables. It is a function from the sample space to, I would say, the real line. In our case, it's discrete, so it's 0 and 1, but it's a function, a mapping from heads equals 1, tails equals 0. That's the random variable we're talking about. Okay, so notice if it takes 1, then it's 50%. But if it's not 1, then let's just say it's 0. Okay, it's 1 minus x. Then it's probability 50% too, because, well, I guess if you add 50% times, like 50% plus 50% is 100. So let's just say in another example, this is what it looked like. So P, 30% probability of getting heads, multiplied by the probability of getting tails, which is 1 minus 30%, And notice the numerators here. The exponents. So the exponent, if this is 0, this is canceled out. This is just 1. Then this becomes 1, and this is what we're talking about, 0.7 here. But if this is 1, this cancels out to be 0, which turns this into 1, and this turns into 0. This turns into 1, which is 0.3. So the x here is mapping the heads or the tails. So the number of successes. So let's say number of successes. In the Bernoulli case, the number of successes is actually 1 or 0. It can only be 1 or 0. And let's generalize this. So in this case, p equals 0.5 here. Well, we can generalize this into px1 minus p1 minus x. And this is the Bernoulli distribution. Now, you might ask, what is the mean of this distribution? What is the mean of this distribution? Now, it comes out to be p. The mean of the distribution becomes p. So if you plotted this Bernoulli, let's say it looks like something like this, the mean of it, maybe it's not a good example because if the mean would be p. Okay, and then the variance turns out to be p1 minus p. Okay? The variance. All right, so now let's talk about the binomial. Now, I gave the example of flipping coins, right? Flipping coins. So the binomial is NP. We got to talk about the assumptions of the binomial real quick. So it's basically a repeated Bernoulli trial n times. And we are assuming the trials are performed independently, meaning the outcomes are independent. What this means is that one trial does not affect the other trial. So if we get a heads, that doesn't affect the probability of getting heads the next time, or the probability of getting tails the next time. It's all independent. Okay? And then probability of success in each trial remains the same. So that means the p doesn't change. P is fixed. It's like in our fair coin example, 50% would be fixed. And then for the random variable, I'm going to abbreviate it for time. X equals the number of success in n trials. Okay? So now that we have the assumptions, let's build it. Well, let's look back at the Bernoulli. It's basically the same thing as Bernoulli, except this term becomes n, and we have a coefficient out front, which I'll explain in a second. So what do we have? We have p to the x, 1 minus p to the n minus x. Notice, I'm going to highlight this in blue. These, when added, equals n, right? Because you're doing x plus n minus x, and the x's cancel and it becomes n. So there's n total trials, but x of them are successes and n minus x are failures, basically. Okay? So, but we must there's a coefficient out front that we're missing. And let me try to explain this more intuitively by giving you guys an example. Okay? So let's just say our n equals 4, and our x equals 2. So let's say, what does this mean? What does this mean? So first of all, this means we flipped a coin 4 times. 2 out of 4 success / heads. If we define heads to be success. So what are the positions? So this is a counting problem, right? So we know that there's 4 trials. There's 4 slots. And let's denote the successes as S and the failures as F. So what are all the possible permutations of 2 successes and 2 failures? Let me show you guys. Let's just say there's SSFF. There's SFSF, SFFS, FSSF, FFSS, and then FSFS. Okay? Let me just double check I did that right. Looks about right. So there's 6 possible ways to do this. And we must multiply what we have right here. We must multiply this by 6. But if we change n and we change x, every time the number is going to change. So how do we find the number we want to find is a number of ways we can permute 2 groups of numbers such that 2 of them are successes and 2 of them are failures, or 3 of them are successes, 1 is a failure, or the n could change. So n could be 5, x could be 3, and then 1 minus x could be 2. So what's the way to do this? So to think about it, I'm just going to give you the answer. The answer is the combinations, okay? In this case, we have 4 slots and 2 successes. What does this turn out to be? This turns out to be 4 factorial over 2 factorial over 4 minus 2 factorial. This turns out to be 4 factorial over 2 factorial times 2 factorial. This becomes 4 times 3 over 2. If you guys don't, let me not go this fast. This becomes 4 times 3 times 2 times 1. This is 2 times 1, 2 times 1. These cancel, so it's 4 times 3 over 2 equals 6 over 2. Wait, I messed up somewhere. Let's see. Let's see here. 4 times 3 is not... 4 times 3 is 12. So that's where I went wrong. I was like, the answer should be 6. I don't know why I'm getting 3. So then it's 6, which is what we have here, the 6 combinations here. And to think about why this is, think about it like this. So what are the number of possible ways to arrange 4 slots? Don't think about the combinations, because think about the permutations between slots. Well, you have, let's just say we have 1, 2, 3, 4. What's the number of ways of arranging four numbers like this? Well, the answer is 4 factorial. That's a permutation problem. 4 could go in here, 3 could go here, 2 could go here, 2 could go here. It's 4 factorial ways of doing this. So that's numerator. That's what we got on the top. That's numerator. But we got to consider something else here. We only have 2 groups, right? We only have 2 groups. And so we got to divide out the fact that we have 2 groups. And we do this. The denominator here is the part where we look at only 2 groups. And that's how you look at it intuitively. So let's go back to our binomial example here. So we got to add this term up here. N, in their case, we have 4 choose 2. And in our case, n equals 4, x equals 2. Well, let's make it more general. Let's just make this n and x. So that's basically the binomial right there. And you might be asking, that's the intuition behind it, but what's the mean of this? The mean turns out to be n times p, and the variance turns out to be let me write this a little bit clearer. Whoops. N times p times 1 minus p. Sometimes people denote 1 minus p as q, so it could be that too. And so that is how you derive the... So let's do an example. Okay? That is the derivation of it. Now let's take this example, this one right here. And let's say p is... Let's say p equals 0.4. Let's just say that. And we get this example here. Let's plug it in. Let's plug it in. So we have it right here. Whoops. What's n? N is 4. X is 2. P is 0.4. X is what? 2. 1 minus 0.4. And then n is 4 minus 2. Let's find the probability of getting this outcome. All right, this is 6, like we did before. 4 to the power 2. I'm going to use a calculator. Sorry. This is 0.16. This here is 0.6. This is 2. 0.6 times 0.6, that should be 0.36. So we times 0.36 times 0.16. Whoops. 0.36 times 0.16 times 6. And we got 0.3454. So in the end of the day, what does this calculate? You know, it's kind of, if you don't think about it, you don't really realize what you're calculating. So let's just say we're flipping a coin. Let's say in statistics, we don't usually know what p is. We don't really know what p is. We're usually trying to estimate p, but let's just say in probability terms, we know p is 40%, right? So we know what p is, so we can plug it into the equation. And let's say in our experiment, what is the probability, given that p equals 40%, that 2 out of 4 coin tosses reveal heads. 2 out of 4 coin tosses. Well, that is right here, 34.56%. That is what the number represents. Now, a little bit of a tidbit here. Sometimes we don't know. Half the time we don't know p. We know through data. We try to estimate p, and it turns out one of the best estimates for p hat is x bar. Okay. And which is the average of the x's. And now it gets kind of confusing because, but it's just the way it is. So, because, yeah, so that's just some statistics for you. But so that's a binomial distribution, and I hope you guys enjoyed. Remember, it's an extension of the Bernoulli distribution, and we got 4 assumptions going on. It's basically a repeated Bernoulli trial n times independently, and the probability stays the same, stays fixed between each trial. So that's it. Hope you guys learned something, and see you guys.